Hello students, Deepak Pandey this side and welcome to Engenius. So far we have covered the features of and design of ideal reactors. Whatever we can discuss about ideal reactor we have already discussed. I mean the design equation of ideal reactors, their comparison, their combination, right? Then the graphical interpretation, the Levenspiel plots. Now I hope you know everything about CSTR and PFR. You know how to compare them. You know in which case CSTR should be preferred, in which case PFR should be preferred. I have also discussed that how to solve the numerical problems based on the reactors, individual reactors and their combination also. Arrangement of reactors, selection of reactors, everything has been discussed so far. Now before going to the next chapters, there are some special topics left related to the discussion of ideal reactors, some modifications in the ideal reactor. So in this class I'm going to discuss those topics only. As far as the gate point of view is concerned, the topics that I'm going to take right now are less important. I'm not saying that they are not the part of gate syllabus, definitely they are. And one or two times questions have been asked based on these topics. So can you guess what still we have to discuss in ideal reactors? The first thing that I'm going to discuss, you remember I asked you two questions, in which case a CSTR can act like a PFR, and I already answered that when you combine a number of CSTRs in series and when n tends to infinity, it practically behaves like an ideal PFR. The other question was the other way of the same question can also be asked in just a reverse manner, that in which case a PFR can behave like a CSTR. So in today's class I'm going to answer that question. So what topics we are going to discuss here is the recycling in reactors. Now normally you won't find this topic in any discussion in any class or in any gate material. So recycling in reactors. And as I told you, conceptually the concept is definitely it is important, and question can be framed based on recycling in reactors. It's not like that recycling of reactors is not in your syllabus. Definitely they can frame a question. Fine. And as you can mark here, if you are sitting in an interview and you are saying that okay, CRE is your favorite subject, and this happens in BARC interviews only, because when you sit in the PSU interviews hardly last for 20 or 25 minutes. 20-25 मिनट से ज़्यादा PSU के इंटरव्यूज़ नहीं होते, whether you talk about HPCL or BPCL or IUCL or ONGC or NALCO, or you just take any PSU, GAIL, you name any PSU, the interviews are not going to last more than 20 minutes. But if you talk about the BARC interview, it can last even for 1.5 hours. Some of my students have shared their experience that their interviews was from 1 hour 10 minutes to 1 hour 30 minutes. In that case, they can ask you the subjects, and if you are saying that sir CRE is my favorite subject, then I have also pointed out some other important things. From CRE, most of the times they ask you questions from the kinetics. Whatever derivations we have done in kinetics, those are going to be very helpful for you for clearing the BARC interviews. This topic is also one of very important topics for BARC interviews as well as for GATE exam also. And this what is the other thing which makes this topic quite important, that most of the students have no idea regarding the recycling in the reactors, because they don't find a proper content based on recycling, why recycling is done, what happens when recycling is not done, these kind of things. In GATE exam there are few questions, and whenever student encounter those questions, what they do, they simply skip the question और आगे बढ़ जाते हैं that ठीक है recycling का क्या करना है. कई बार क्वेश्चन के आंसर को रट लेते हैं, सॉल्यूशन पढ़ के समझ लेते हैं, बट कॉन्सेप्ट नहीं पता तो कोई फ़ायदा नहीं क्वेश्चन करने का. ठीक है, अगर आप सिर्फ क्वेश्चन का आंसर देख के सोच रहे हो कि नहीं ये एक दो क्वेश्चन को ऐसे ही पढ़ लेते हैं, उसका कोई फ़ायदा नहीं, उससे बढ़िया छोड़ दो, राइट. बट इफ़ यू नो द कॉन्सेप्ट देन ओनली it is going to be helpful for you, right? So this is again a very important topic. So in this class I'm going to discuss the recycling in reactors. So when I'm talking about reactors, it can be a CSTR or it can be a PFR, and you can do recycling. We have also discussed the concept of recycling in process calculation, with reaction also, without reaction also. So there also I have defined that what is the recycle ratio, what is recycling, why recycling is done. Those things we have also discussed there. Okay, so let us start with the recycling in a CSTR. Actually, what recycling does actually, whatever be the type of reactor, what recycling does, you should write one point. Recycling increases back mixing. Getting my point? Recycling increases back mixing. What is the meaning of back mixing? You know that a CSTR is also called a back mix reactor. Back mixing means a reactor, a molecule which is just about to leave the reactor. There are chances that the molecule was just about to leave the reactor and now it is not leaving the reactor. It has, due to infinite mixing, the molecule just came somewhere inside, the molecule was just lost inside the infinite mixing of the reactor. निकलने वाला था but उससे पहले उसको वापस खींच लिया और फिर से reactor के अंदर उसको घुमा दिया. Like that. That is called infinite mixing. Now, we know that there is no mixing in the PFR, but whenever you do recycling, what it does actually, the recycling increases back mixing. But if you talk about the recycling in a CSTR, that is our topic. Recycling in a CSTR. You know that CSTR is already having infinite mixing. We already discussed these points that a CSTR has infinite mixing. I hope you are comfortable with this, right? An ideal CSTR already has infinite mixing. And what mixing does actually? I told you that mixing leads to uniformity. Whenever you do mixing, it leads to uniformity. It leads to decrease in the concentrations. You know that in a CSTR, the concentration values inside the reactor are constant and at lower values. While what happens in a PFR? In a PFR, there is a gradual decrease because there is no mixing in a PFR. So, an ideal CSTR already has infinite mixing or infinite back mixing, you can say. Mixing, back mixing, right? Back mixing. So, conceptually, recycling should not affect the performance of the reactor. Recycling should not affect the performance of the reactor. Are you getting my point? That what recycling is doing basically, the recycling is trying to increase the back mixing. But we know that in a CSTR, there is already infinite mixing. In a CSTR, the infinite mixing is already existing. So mixing पहले से infinite है, and then you are again recycling, then there should not be any effect on the performance of the reactor. Means, what is recycling in a CSTR? Suppose this is a CSTR. And let for simplicity, let a first order reaction is taking place. For simplicity only. It can be proved for any order, but for simplicity, we have the relations for first order of a CSTR reaction taking place in a CSTR. So I am taking the example of first order. Suppose it is a Ca0. The conversion is 0. Suppose the volume is V. Suppose the reaction taking place is A giving B, such that minus Ra is equal to Kca. And of course, like every time whenever I am proving anything, it is always helpful, it is always easier for me to prove the things in case of constant volume reaction system. Okay, so again it is constant volume reaction system also. You are having some exit concentration Ca, volumetric flow rate, nu naught. Let first order reaction is taking place. What is the performance right now? What we have studied? This is a CSTR without recycle, right? This is a CSTR without recycle. And I hope you all remember that Ca can be written as Ca0 divided by 1 plus K tau. For a first order reaction, it can be written like this. Or, you know that what is the design equation for a first order reaction? Xa by 1 minus Xa is equal to K tau. This was the design equation. Same thing. These are both are same thing. You can obtain one relation for other. This is what we have already discussed. Now in this CSTR, we assumed infinite mixing. There is no recycle. Let us do one thing, that in the same reactor, let us recycle. Let us assume recycling in the reactor. Now what is basically recycling? It means that you are taking some part of the liquid which is leaving from the reactor and recycle it back and mixed with the fresh feed. This is called recycling. Recycling means what? Recycling means whatever is leaving from the reactor, some part of that, not the entire part. It depends actually on the recycle ratio. But what is recycle actually? This is a reactor. The same reactor, suppose I have the same reactor of volume V, reaction mixture is having this volume. The inlet concentration is Ca0. Let me make this diagram so that I can create some space on the left hand side. So we have this reactor here. Okay, reaction mixture, volume is V. Infinite mixing is there, I told you, as it is there in case of a CSTR. Volumetric concentration Ca0, volumetric flow rate U0. Again the same reaction A giving B, and I am assuming first order. I am proving this for first order reaction, but it is also valid for other order of reactions. And then this is the stream C. Now what is recycling? The recycling means a part of the exit stream from the reactor, a part of this stream is taken back and then it is recycled and mixed with the fresh feed which is coming. This is basically called recycling. As I discussed in process calculations also, that recycling operations should always be discussed, should always be analyzed at steady state. So please don't assume unsteady state here. We are dealing with the things at steady state. So please write somewhere that we are dealing with the things at steady state. It means nothing is changing at a given location with respect to time. I hope all of you understand that whenever there is a recycle, I can consider this system for writing balances also. Right? This is one system. We have done this in process calculation, that how to select system in recycling. That's why I told you that. That's why I told you there are small things, little things related to the concept of process calculation in each and every subject. Now you may ask, sir, what is this system, how you are selecting these boundaries? That is why I say that before watching any lecture, before watching any subject of chemical engineering, if you are not comfortable with process calculation, then you will feel that okay, something is missing, something you are not able to understand, right? We call this point as the mixing point, right? Okay, what else? We have this splitter also. This is a splitter, and then you have this reactor also. These are the system on which you can write the balances. Now we are dealing with steady state system and we are dealing with constant volume reaction system. Now if you are saying that, sir, this nu naught and this nu naught should not be same, तो आप गलत हैं. If you are thinking that this nu naught is why this nu naught is same, the thing is it is constant volume reaction system. At constant volume reaction system, you know that the volumetric flow rate should be same. The inlet and the exit volumetric flow rate should be same. And if I am not taking these volumetric flow rates to be same, then definitely there will be accumulation inside the system, because it is CVRS and it has to be steady state also. The other thing, that the concentration, because this is a splitting point. What is the concentration inside the CSTR? The concentration inside the CSTR is same as the concentration at this point. What is the concentration at this point? It is Ca. The concentration inside the reactor, Ca. The concentration of the stream which is recycled, Ca. Why? Why? Again the concept of process calculation. When a stream is simply splitted, it's not a separator, a stream is splitted into 2 or 3 or more parts. When a stream is splitted into 2-3 parts, the concentration always remains same. Fine. So this is Ca. Okay. Now let us suppose the flow rate of this stream, you can give some name to this flow rate, right? Let us say that this is the flow rate of the recycle stream, right? So this recycle stream, this is the volumetric flow rate of the recycle stream basically. Okay, this recycle stream goes like this and then it combines with this reactor. Now when two streams of different concentration are mixed, this is Ca0, this is Ca. When the two streams of different concentrations are mixed together, then they are going to form a new concentration. So here the concentration cannot be Ca0, it cannot be Ca. Let us call this concentration as Ca1. And can you tell me that what is the volumetric flow rate of the stream which is entering the reactor, it is very simple. By applying balance at the mixing point, it is nu naught plus nu R. The volumetric flow rate is nu naught plus nu R. Fine. This is called the recycling in any reactor. Now in this case we have a CSTR. Now recycle ratio is defined as, it is denoted by R, it is defined as the stream which is sent as the recycle stream, the flow rate of this stream. So R is equal to the molar flow rate of the recycle stream divided by the molar flow rate of this stream, the exit stream. You can call that stream as, let us call that stream as F, you can say, let's call that stream as FA. The molar flow rate of this stream and the molar flow rate of this stream, that is the recycle ratio. It can also be written as, because the concentration of these two streams are same, so it can also be written as nu R by nu naught. That is equal to the recycle ratio. Means the flow rate of this stream divided by the flow rate of this stream is called the recycle ratio, and therefore can I say that nu R is equal to R nu naught? I hope you don't have any problem here. Fine. Now we have to compare that the design equation for the reactor in this case was this. What is the design equation for the reactor here? I already told you logically how you can explain this, that in a CSTR there is infinite mixing. Whether you do recycle, whether you not do any recycle, whatever be the case, it is not going to affect the performance of the reactor. But let us also prove it mathematically. That's why I am doing this. So recycle ratio is defined like this. So accordingly, I have the equation nu R is equal to R nu naught. Now let's write the balance on the reactor. Balance of A on the reactor. So I'm trying to write balance on reactor. I'm not writing the balance for the overall system. Please note that is important, that the reactor is only this part. I am writing the balance on this reactor. Okay. Balance of A on the reactor. So what is entering here? What is entering? Nu naught plus nu R, which is R nu naught, multiplied by the concentration CA1. Getting my point? This is what is entering. And please note that CA1 is not known to us. CA1 I have introduced myself. CA1 मैं खुद से लेके आया था ना. अगर CA1 को मैंने खुद introduce किया तो later I am going to replace CA1 with the known quantities, right? So nu naught plus R nu naught into CA1 which is entering. What is the balance? What is balance? In minus out minus reactor is equal to 0 because I am doing steady state balances, right? इसलिए मैं कह रहा हूँ कि प्रोसेस कैलकुलेशन के जो कॉन्सेप्ट्स है बहुत छोटे छोटे बेसिक कॉन्सेप्ट्स, दे आर इंपॉर्टेंट एंड दैट इज व्हाई I always teach process calculation before teaching any other subjects. Most of the even the faculty, the students, they say sir mass transfer पढ़ा दो, sir CRE पढ़ा दो पहले, sir heat transfer पढ़ा दो, एंड समझ भी जाते हैं पता नहीं कैसे. मैं उनको मास ट्रांसफर पढ़ा दिया, स्टूडेंट से सर समझ आ गया, समझ आ भी जाएगा, दैट इज नॉट अ प्रॉब्लम. But these small details they are not going to learn unless you know about process calculation. And if you are saying that sir I am not able to understand process calculation but somehow I was able to understand CRE, I was able to understand mass transfer, then you are lying. You are not able to understand neither process calculation nor mass transfer. आपको कुछ नहीं आता इसका मतलब. अगर आपको process calculation ही नहीं समझ आ रही तो how you can learn the other subjects, how you can learn the reaction engineering? You are just trying to remember the things, and as I told you in GATE exam you have to remember the things, but try to keep the formulas, the facts that you have to remember as minimum as possible. Try to learn the things with the derivations, with the conceptual knowledge, so that you can remember those things easily with the help of the story, with the help of the derivation. But there are some facts which you have to directly remember. तो वो चीज़ें जितनी कम होंगी वो भूलने के चांसेस उतने कम होंगे. अगर आप हर चीज़ रट के ही चलोगे, हर चीज़ रटते ही रहोगे, इसका फॉर्मूला ये, इसका फॉर्मूला इसको ऐसे सॉल्व करना है, इस तरह के अगर इसको रटते ही रहोगे ना तो डेफिनेटली आप भूल जाओगे. एक सब्जेक्ट पढ़ोगे दूसरा भूल जाओगे. तो किसी भी सब्जेक्ट में कोशिश ये करनी है दैट यू लर्न द थिंग्स अलॉन्ग विद द डेरिवेशंस, अलॉन्ग विद द कॉन्सेप्ट्स, अलॉन्ग विद द बेसिक नॉलेज, सो दैट even if you forget then you can write the derivation and then again you can derive the things. Okay, so CA1 in minus what is leaving the reactor? Please note leaving the reactor. I'm not talking about leaving here, leaving the reactor because I'm applying balance on the reactor. So what is leaving? Okay, this volumetric flow rate is nu R. This volumetric flow rate is nu naught. So what is this volumetric flow rate? Nu R plus nu naught. And obviously this and this volumetric flow rate should be same because we are dealing with CVRS as before. So nu naught plus R nu naught multiplied by what? Multiplied by CA in minus out minus reacted. And what is reacted? Minus RA into V, and minus RA is equal to KCA. KCA into volume of the reactor is equal to 0. I hope all of you are comfortable with this balance equation on the reactor. Now everything is fine here. The only thing that which is making a problem is the new concentration that I have introduced, that this concentration which is CA1. So let us see if something is getting cancelled, yes or no. R nu naught CA1, nu naught CA plus R nu naught CA. Okay, so let us first of all replace this unknown quantity, because CA1 should be replaced. CA1 should be replaced with known values, right? Because it's not a known quantity, it's not given to us. I just introduced it with known quantities. See, whenever a stream is splitted into 2-3 parts, the concentration remains same. But whenever 2 or 3 streams are mixed together and they are having different concentration, then the concentration of exit stream will 100% it will be different. So that is why this CA1 cannot be equal to CA0, CA1 cannot be equal to CA. It's a new thing. Let us replace CA1 in terms of CA0 and CA. So how to replace CA1? Write balance of A. Everything is about balance. Balance of A on the mixing point. Everything is related to the balance. If you know how to write balances on the mixing point, if you know how to write balances on any system, then these things won't be very much difficult for you. So how to write balance on the mixing point? What is coming from here? In, what is coming in? CA0 into nu naught. What is coming in from here? Nu R, which is R nu naught into CA, everything is known till now, is equal to nu naught plus nu R, that is nu naught plus R nu naught multiplied by CA1. And from here you can now take the value of CA1 is equal to CA nu naught plus R nu naught CA divided by nu naught plus R nu naught. And I hope nu naught is getting cancelled, you know that. And this is equal to CA. Nu naught is getting cancelled. CA is common, so it is R. Okay, CA into, okay, nu naught is getting, so CA plus RCA, right? So you are taking R plus 1. And what is the CA1 is equal to, what is CA1? CA1 is coming out to be equal to CA. Now there is some problem here. Balance of A on the reactor, that is written as nu naught plus R nu naught into CA1. Yeah. Volumetric fluid that is going into the reactor minus what is leaving from the reactor, that is nu naught plus R nu naught, that should be same. CA is equal to the reactant minus out minus reactor is equal to 0. Everything is fine here. Balance of A on the mixing point, it's what is coming plus what is coming from here, which is nu R is equal to R nu naught into CA is equal to nu naught plus R nu naught into CA1. So CA1 is CA, okay, I think there is some problem here. R nu naught CA, this should be CA naught. I hope now it is fine. CA1 is equal to CA naught into nu naught plus R nu naught CA divided by nu naught. Okay, that was the mistake which was happening here. So CA1 is equal to CA naught. Nu naught was getting cancelled, right? So CA naught plus RCA divided by R plus 1. That is the value of CA1 in terms of known quantities. Now if that value, if you substitute here, then what you are going to get? You can put the value of CA1 here and let's see what are you getting. What are things are getting cancelled or not, or you're getting the same design equation or not. That is important to derive here. So if you put the value of CA1 in this equation, then let's see what we are getting. R plus 1 and R plus 1 from here is going to be cancelled. So it will be nu naught. I'm directly writing the final equation which you will be getting. So nu naught into R plus 1 and R plus 1 will be cancelled into CA1, which is CA naught plus RCA. Right. So I have eliminated this unknown quantity which is CA1 minus nu naught plus R nu naught multiplied by CA minus KCAV is equal to 0. So now this equation, the design equation of the CSTR, is present in terms of known quantities. I have replaced the unknown CA1 by using the balance at the mixing point. Now you are going to find that few things are getting cancelled. It will be nu naught CA naught plus RCA nu naught, and here you will be having R minus RCA nu naught. So it is nu naught into CA naught, nu naught into CA naught, that is from the first term, and then RCA nu naught and minus RCA nu naught gets cancelled, and this becomes nu naught CA minus KCA into V. Now here only you can identify that the rate relation remains same. V by nu naught can be written as tau, and here also you are going to get CA is equal to CA naught divided by 1 plus K tau, or XA by 1 minus XA is equal to K tau. Fine. So what is the conclusion from this mathematical derivation? The conclusion is same which I am writing here, means in a CSTR, whether you have no recycle, without recycle, if there is no recycle, then what is the recycle ratio? What was the recycle ratio? The flow rate of the stream divided by the flow rate of the stream which is leaving the overall system. So if there was no recycle, the recycle ratio value is 0. Suppose there is some recycle and the recycle ratio is equal to 2. And suppose there is a third case when there is very high recycle, when the recycle ratio is equal to 50 or 100. What you can say about the conversion obtained for the reaction in all these three cases for various values of CSTR, your various values of recycle ratio? Your answer should be that the conversion remains exactly same. Why? I have proved here. So you can write the conclusion that whatever be the recycle ratio in a CSTR, whether it is 0, low or high, the conversion obtained or the whatever performance of the reactor is there, it is not going to be affected. In an ideal CSTR, whatever be the value of recycle ratio, whatever be the value of recycle ratio, means high recycle, low recycle or no recycle, whatever be the value of recycle ratio, means you can write in the bracket 0 means there is no recycle, low 2, 3, 4, high 50, 60, 100 or even higher, whatever be the value of recycle ratio, the conversion obtained, or you can say the performance of the CSTR, the conversion obtained remains same. The conversion obtained remains same. Obtained remains same. Fine. So that was the discussion of recycling in a CSTR. तो कुल मिला के CSTR में recycle करने का कोई फायदा नहीं है, and that is why recycling is not done. Even in practice, we do not follow recycling in a CSTR. So I hope this discussion of the recycling in one particular type of reactor is clear. Now there was a question based on this discussion in GATE 2015. In fact, it was exactly this question which I have proved here. You can also save some time in proving this question. Actually what I did, I put the value of C, first I found the value of CA1 and then put it back here. Actually you can also write this equation directly, because what is this? This is nothing. This is nu naught into CA naught plus RCA, right? You can say that nu naught is coming from here, nu naught into CA naught, and what is coming from here? This is R nu naught into CA. So nu naught into CA naught plus R nu naught into CA. You can directly also write these things, okay? So, okay, I hope this discussion is clear. Now let us move to the second type of reactor along with recycle, that is PFR with recycle. And when we talk about recycle reactor in reaction engineering, it is most of the time PFR with recycle, because I proved here right now that there is no meaning of CSTR with recycle. We are not having any advantage or disadvantage also. Of course, if you are doing recycling in a CSTR, it may add up to the cost of pumping and recycling. So there is no advantage of recycling in a CSTR. So generally, if there is a question and it says that there is a recycle reactor, the first thing that should come to your mind should be that it must be a PFR with recycle, because there is no meaning of recycling in a CSTR, logically also, conceptually also, and mathematically also. Because I already told you that there is infinite mixing. And what is the purpose of recycling? The purpose of recycling is to increase the extent of mixing. Recycling increases mixing. Recycling increases back mixing, right? That is the thing. That is the purpose. Okay. Now let us discuss the recycling in an ideal PFR. That is the second type of recycle reactor. Recycling in an ideal PFR. We know that, पहले इसको qualitatively discuss कर लेते हैं. The qualitative discussion is also very important. We already know that in a PFR, the recycling, the mixing, the extent of axial mixing is equal to 0. We have discussed this, right? That in a PFR or in an ideal PFR, the extent of axial mixing is equal to 0. I hope all of you remember this, that extent of mixing in an ideal PFR is equal to 0. If recycling is done in a PFR, so what you are doing basically? In a PFR, I told you that there is no mixing of the plugs. Each plug is behaving like an individual reactor. If you are mixing the fluid which is leaving from the reactor to the fluid which is coming into the reactor, it means what you are doing? You are mixing the more converted liquid to the less converted liquid. Means what you are doing? You are actually increasing the axial mixing, which was initially 0, in an ideal PFR there is 0 mixing. But if you are recycling, means you are mixing the liquid which is highly converted to the liquid which has 0 conversion. It means you are increasing the extent of mixing in the PFR. So that is what is happening here. If recycling is done in a PFR, we are increasing the extent of mixing. The extent of mixing in the reactor. Now what should be its effect? Means we are increasing the extent of mixing. Means what we are doing? I told you that there are two extremes. In the case of ideal reactor, there are two extremes. One extreme is 0 mixing and one extreme is infinite mixing. But in the 0 mixing case, in the case of ideal PFR, if you are recycling, means you are bringing in some extent of mixing. Means what should be the effect? What do you think? In a PFR, if you do recycling, suppose these are the two ends of the world. This world is PFR with 0 mixing. This world is CSTR with infinite mixing. If you are recycling in a PFR, means you are doing some mixing. And if you are doing some mixing, it means that from this end of the world, you have started traveling to this end of the world. And now if you have some mixing in the PFR, you are here, you are not here, you are present here. Means a little bit of CSTR character will be introduced in the PFR. That is the effect of recycling in a PFR. Let me write here. We are increasing the extent of mixing in the reactor, and hence the behavior of PFR, the behavior of recycle PFR, because PFR is PFR, hence the behavior of recycler PFR becomes closer to the CSTR, becomes closer to the CSTR. This is the answer of my second question, that in which case a PFR can behave like a CSTR. So if you do recycling, what is the logical explanation? See, in the recycling, you are mixing the more converted to the less converted, and you are increasing the extent of mixing. And mixing is the idea of CSTR. Mixing is the characteristic of CSTR. If you are increasing mixing in a PFR by recycling, then it means you are slowly shifting towards the CSTR behavior. In which case you are going to behave exactly like a CSTR. Like I told you that if CSTR are connected in series, it is behaving close to the PFR. But if you want exact PFR behavior, then you should have infinite number of CSTRs connected in series, right? So what is the meaning here? And hence the behavior of recycle PFR becomes closer to the CSTR. If the recycle ratio, now what is the recycle ratio? The same definition of recycle ratio which I gave in the previous discussion. If the recycle ratio tends to infinity, then the system is not the reactor only, system is the entire system. Then the system behaves exactly like an ideal CSTR. Then the system behaves exactly like an ideal CSTR. Exactly like an ideal CSTR. I hope the idea must be clear. Idea must be clear. Now there is one more very, very important conclusion from this. I am saying that if you are increasing the recycle, slowly you are increasing the recycle, you are going to more closer to the behavior of CSTR. What does it mean? It means that it's now in your control. By controlling the recycle ratio, you can have a different combination of PFR, different reactors, which can lie anywhere between the two. This is the PFR, this is the CSTR. You have low recycle ratio, you are having a reactor whose performance lies somewhere here. You have some high recycle ratio, you are having a reactor whose performance lies here. So you can obtain various performance of reactors by changing the recycle ratio of a PFR. That is one conclusion, that different performances of reactor means you can have different, you want more CSTR behavior, less PFR behavior, you want more PFR behavior, less CSTR behavior, that all these combination can be obtained by changing the recycle ratio. So you can write down that also. Different performance of the system of the reactor can be obtained. Reactor can be obtained by changing the recycle ratio. By changing the recycle ratio. Write down, by changing the recycle ratio. So it's now under your control by changing the recycle ratio, right? It's now under your control that what behavior you want from the recycle reactor. You want behavior more closer to the CSTR, keep very high recycle ratio. You want the behavior more close to the PFR, keep low recycle ratio. So ultimately, by doing more and more recycle, you are increasing the extent of back mixing and you are moving closer to the PFR. Now my question is, if I am moving closer to the CSTR, if you are increasing the recycle ratio, on increasing the recycle ratio, I'm writing in short, on increasing the recycle ratio, we are moving closer to the CSTR behavior. We are moving closer to the CSTR behavior. Moving closer to the CSTR behavior. And do you know that what is the behavior of a CSTR? I hope if you are continuously following the lecture, you remember also. What is the behavior of a CSTR? If the order of a reaction is greater than 0, which is in most of the cases, in most of the practical cases, the order is only positive. If the order of the reaction is greater than 0, then a CSTR gives less conversion than PFR. Very, very important point I am going to discuss. If the order of the reaction is less than, or the order of the reaction is greater than 0, it is positive, then the CSTR conversion is always low. It means if you are recycling, on increasing the recycle ratio, we are moving closer to the CSTR behavior, and hence a recycle reactor should give low final conversion, should give low conversions as compared to the PFR of the same volume. Low conversion as compared to the PFR itself. Are you getting my point? As compared to the PFR itself. This is only logical explanation. I'll give you the numerical explanation, the theoretical, the derivations also. Fine. So what is the extent of backmixing? What is the extent of this recycle ratio in your recycle PFR? In that case, you can control the behavior of your recycle reactor. But now the question arises that if on increasing the recycle ratio, I am moving closer to the CSTR behavior, then it means that the conversion obtained now at high recycle ratio will be low. The volume required of the reactor at high recycle ratio will be more. Then why recycling should be done? If I am getting less conversion on doing recycle, then why recycling should be done? Fine, that is my question, and that you will be understanding once we do this derivation. So let us assume that there is a PFR with recycle, and we are having a CVRS system at steady state. We are having this, and then there is a PFR with recycle. Of course, if it is a PFR with recycle, then something is coming in here, something is leaving, and like we did in the CSTR case, I'm taking a stream out of here. Suppose this volumetric flow rate is Q0, and at steady state CVRS system, I should have this also equal to Q0. And what is the definition of recycle ratio? This is the recycle stream, and this flow rate, can I write directly that this flow rate is equal to R into Q0? Because what is R? R is the recycle ratio, and R is defined as the volumetric flow rate of this. Let us say that this volumetric flow rate is equal to QR. I can also use a different symbol, nu, that is not a problem. So QR is equal to RQ0. This is K0. This is what is happening inside the recycle PFR. But definitely, this concentration is a different concentration. Let us call this concentration as CA0. This concentration is CA or CAF. Let us call it CAF. And this concentration is something else. Let us call this concentration as CA1. Fine. Okay, that is the scenario. And this is your PFR without, if you're talking about without recycling, this is the PFR, and suppose the volume of the PFR or volume of the reactor is equal to V. Some reaction is taking place, and the reaction is A giving B, and the rate is minus R. I'm not assuming a first order here. I can derive it without assuming first order also, not a problem. This is the scenario of a PFR with a recycle. Now the thing is, you know that whenever you write balance on a reactor like this PFR, you cannot select the entire PFR to write the balance. I told you why. It must be uniform. Now that this recycle PFR is not uniform, so let us select a balance. Let us select an element here, a small element, and let us write the balance. The small element is having a volume equal to dV. Now what is entering in the reactor? In this small element, what is entering? From here, you can have the concentration entering equal to Ca. Please note this Ca is not equal to Ca1, Ca is not equal to Ca0, Ca is not equal to Cf. Ca is entirely different. And what is leaving? As we did for the derivation of ideal PFR, the leaving is Ca plus dCa. You can also ask that, sir, why you are doing all the derivation here in terms of concentration while we did the previous derivations in terms of molar flow rates? The answer is right now what I have written here, what I have assumed here, CVRS. So in CVRS, you can do the derivations in terms of concentration. Another explanation, deriving the results here is easier as compared to the deriving the results for general system, for variable volume system in case of recycle reactors. So I'm not going to derive that one. I will be deriving this one, and based on the same analogy, I'm going to give you the formula which will be valid for both CVRS and VVRS. However, for variable volume reaction system also, the formula, the concept, the relation can be easily derived, but we are not doing that. Let's not complicate the discussion very much. I want to keep the discussion simple, and also at the same time I want to convey all the important information to you. So QR is equal to RQ naught. Now how to write the balance equation? What is the balance equation? Let us write the equation. It says we have already written this kind of balance equation for the ideal PFR, so I hope that won't be very much difficult for you. And also let us also write the balance on the mixing point also, so that I can replace the value of concentration later. So what is the balance at the mixing point? Let us first write the balance here at the mixing point, the balance on A. What is coming? Q naught into Ca naught. From left hand side, what is coming from the recycle stream? That is plus R into Q naught. I told you that all these concentration remain same because this is a simple splitting point, is equal to Ca1 multiplied by Q naught plus RQ naught. So that is Q naught into R plus 1. I hope all these things are clear to you. From here you can also get the value of Ca1, because you know that Ca1 is something which we will be replacing later. So that is QCA naught plus RQ naught CAF divided by Q naught R plus 1. It means the value is Ca naught plus R CAF divided by R plus 1. That is, if you volumetric flow rates are getting cancelled, that is Ca naught plus R CAF divided by R plus 1. It is simple balance, simple mathematics. Fine. Now let us write the balance on this element for the PFR. This is just to replace the Ca1, जैसा पहले replace किया था वैसे यहाँ पे भी replace कर देंगे. Balance on the small element. Why I am not writing balance on the entire reactor? Because it is not uniform, and I already told you that what is the criteria for selecting the region as the system. The region must be uniform. Now this entire region is not uniform. I am assuming a very thin element here. So balance on the thin element of volume dV. कैसे लिखेंगे balance? What is coming in? Ca multiplied by the volumetric flow rate. And what is the volumetric flow rate here? The volumetric flow rate here is Q naught plus RQ naught. So here the volumetric flow rate is R plus 1 into Q naught. The same volumetric flow rate will be everywhere because it is a constant volume reaction system. So R plus 1 into Q naught, that is the volumetric flow rate entering at this end of the element, multiplied by Ca. Minus the volumetric flow rate should not change. So R plus 1 multiplied by Q naught, but the concentration is going to change, that is Ca plus dCA. Don't think that this is a new kind of derivation. This is exactly same derivation which you did in case of the ideal PFR without recycle. The only thing which has changed here is one more stream is coming in. So due to this, the volumetric flow rate is going to increase. The volumetric flow rate which is entering the reactor will be more as compared to the volumetric flow rate which is present in the fresh feed, and also this concentration is going. बस ये दो बातें हो रही हैं. The volumetric flow rate is increasing and the concentration is changing. So for change of concentration, I am writing the balance on the mixing point, and hence I can find the value of this new concentration with respect to the known values, and rest everything is same. How to write balance? There is nothing has changed here. Is equal to in minus out minus reacted. So where is minus reacted? Minus Ra into V. What is V now? V is the volume of this entire reactor, but I am writing the balance on this element, so it should not be V, it should be dV, minus Ra into dV, and because it is steady state, the accumulation term is 0. तो अगर देखो, if you are writing the balance by understanding like this, then आप ये चीज़ें नहीं भूलोगे. लेकिन सोचो अगर इसको भी रटना पड़ गया तो कैसे होगा? If you are even trying to learn these things, then कुछ नहीं होने वाला, सारी चीज़ें भूल जाओगे. That is why units, balance, right? Balance must be clear. mass balance or energy balance में if you have difficulty in mass or energy balances, then your basics are weak. They are going to help you a lot at different points in each and every subject. And as I was teaching process calculation, I told you that the weightage of process calculation is only 4 marks. But its importance in understanding of the other subject is very crucial, very crucial. Okay, so this was the scenario. A lot of things are getting cancelled here, right? And I hope you'll be able to integrate this equation. After integration, what you are going to get? dv will be integrated from 0 to v, and you are going to get that v by q naught. V by q naught means that is equal to tau of this reactor with respect to this volumetric flow rate. Tau is equal to 1 plus r, in fact minus r plus 1. Minus will be there because we are writing in terms of concentration and then upper limit, lower limit, those things. CA1 integral CA1, where is CA1? Because CA1 will be higher and CF will be lower, so that is why there is a negative sign. dCA by minus RA. dCA by minus RA. Fine. And what is CA1? CA1 is this. Okay. So this is how you can design V by Q naught is equal to tau. I'm writing here so that it will be visible, more visible, minus R plus 1 integral of CA1 to CF, CA1 to CAF dCA by minus RA. Now this is the equation for a recycle reactor for CVRS system. Fine. That is a relation for CVRS system in a recycle reactor. Okay. One more thing, that what is the relation if you discuss the same thing in case of VVRS. Now I'm not going to prove that. Of course, if you are proving the relation for VVRS, just use molar flow rates instead of these concentrations, because that will be valid even if volume is changing. Now in the recycle reactor, if volume is also changing, then the process of derivation becomes more complex. So let's not do that. Okay. Right. So that is the relation in case of CVRS. Please write that it is only valid for CVRS. I will also give you the relation for VVRS systems. Fine. Now let me rearrange this equation which I am writing here, and let us write this equation as 1 plus R CA naught, CA1, right? 1 plus R means Q naught plus RQ naught. Let me rewrite this equation: Q naught plus RQ naught into CA1 okay, that is equal to what is what is leaving, what is coming in? The coming in is Q naught into CA naught, and what is coming in from here? That is RQ naught into CAF. Right. What I'm trying to do, I'm trying to write a relation so that I'll be able to explain the graph of this recycle reactor quite easily. And if you see this relation becomes equal to CA naught plus RCA1, right? CA naught, Q naught, CA naught plus Q naught is getting cancelled from everywhere, RQ naught, CAF, and then if you add and subtract, plus RCA naught and minus RCA naught, and then you have Q naught plus RQ naught into CA1. Now let us cancel the value of CA1 from everywhere, and then you are getting R plus 1 CA1 is equal to CA naught plus RCAF plus RCA naught minus RCA naught. Right. So I hope there is no problem here. Now I can write this relation as 1 plus RCA naught, CA naught into 1 plus R, and then the relation can be plus R times CAF, R times CAF. So I have used this one and this one. So R times CAF minus CA naught. I hope the idea is clear. R times CAF minus CA naught is equal to R plus 1 into CA1. From here, I am going to get a relation that CA naught minus CA1, CA naught minus CA1, CA naught minus CA1 divided by CA naught minus CAF. CA naught minus CAF. This relation, what is this? CA naught minus CA1. CA naught minus CA1, that is okay, and divided by CA naught minus CAF. Can you tell me the relation becomes equal to, I guess it will be equal to R by R plus 1, right? CA naught minus CA1 is equal to R by R plus 1. Let me check this again. CA naught minus CA1, so that is 1 plus R into CA naught minus CA1, and that is this, must be equal to R into CA naught minus CAF. Yeah, fine. So CA naught minus CA1 by CA naught minus CAF is equal to R by R plus 1. This is one relation. Why I am writing this relation? So that I'll be able to explain the graph easily. Okay, the formula for recycle reactor is there. Now let us understand that what is the importance of recycling. I already told you that for most of the reactions which are having higher order greater than 0, the recycling is not going to give you any advantage, because your behavior of the system is becoming more closer to the CSTR, and then you will be getting less conversion. Then why we are doing the recycle? That I am going to explain with the help of this graph.